Welcome to the another video on VLSI design. In this video, we are going to discuss static CMOS inverter DC characteristics. The reason why we call here static CMOS inverter is because this is an inverter circuit and we are going to apply signals, static signals, just logic 0 or logic 1. So this complete inverter is tested for static signals. Therefore, this characteristics is labeled as static CMOS inverter DC characteristics. And the reason why we have here DC is because we apply here DC voltages at the input and measure the voltages, DC voltages at the output. And here we are going to plot inverter Vout versus Vin characteristics. Before going to the drawing of inverter characteristics, let us try to understand CMOS inverter and its working principle. So this is the CMOS inverter circuit, and here in this circuit we have shown the substrate connection for both N-channel transistor and as well as P-channel transistor. The input signal is applied for the inverter circuit is labeled as Vin. Vin means it's the input voltage which is applied with reference to ground. And here we have a PMOS transistor. PMOS has got totally 3 terminals. The fourth terminal is implicit, which is substrate, but here we have shown both substrate terminal as well. The substrate terminal for PMOS is going to be having an arrow mark which is outward, and the substrate is connected to the source, whereas the source is again for the PMOS is tied to the VDD. As we know that the transistor for a PMOS transistor, the terminal that is connected to high voltage is source, whereas for the NMOS transistor, the terminal that is connected to ground or low voltage is termed as source. So once we identify source terminal for both PMOS and NMOS transistor, it's very easy to identify the drain terminal. So the other terminal is going to be the drain terminal here, and even here for NMOS this is going to be drain terminal. Notice here the drain terminals of both the PMOS transistor and the NMOS transistor with reference to CMOS inverter as a common point here. And here we take the output, and the output is measured with reference to the drains of both the transistor and with reference to ground. Alright, with that the gates of both transistors are connected, and that's where we apply the input voltage. The other voltages which are important in this inverter circuit is VGSP and VGSN. VGSP is nothing but the gate to source voltage for the PMOS transistor. That is the voltage measured between the gate terminal and the source terminal of the PMOS transistor. Similarly, VGSN is nothing but it's a voltage measured between the gate and the source of NMOS transistor. With reference to this circuit, Vin and VGSN both are going to be equal. These two voltages are equal. Similarly, the VDSN, the drain to source voltage of NMOS, that's voltage measured between the drain and source of NMOS, that is labeled as VDSN, which is equal to Vout here. So both are equal to each other. So let me write it here. At the input side, we have noticed V in, which is equal to VGSN, whereas V out equals VDSN. The other voltages also important, namely the VGSP. Let us derive the expression for VGSP. Shortly we can write VGSP expression as Vin minus VDD. So we can write this, we are going to derive this later on. However, I am going to write direct expression for VGSP as Vin minus VDD. Similarly, we can write expression for VDSP as well. That is the voltage measured between the drain and source of PMOS device. So VDSP equals V out minus VDD. This also will be derived later on. VDSP equals V out minus VDD. So these expressions will derive it and show later on, but for time being, I've shown here the direct expression. So this circuit overall is a CMOS inverter circuit, and let us try to understand the operation of this for input as 0 volts and 5 volts, only two levels. When input is equal to 0 volts, let us see which transistor is going to be on. VGSP is now, it is a VG minus Vs, which is minus 5 volts. This value is going to be minus 5 volts. Whereas VGSN, we have a 0 volts here and a 0 volt here, 0 volts here. So VGSN is going to be 0 volts. Therefore, N device is off because its VGSN is at 0 volts. P device is on because VGSP of P device is at minus 5 volt. So this is on. Now once PMOS is on and NMOS is off, the power supply is connected to the output. Therefore, output goes to VDD. So this is for the input 0 volts. The output goes to VDD. Let us try with other voltage. When input is increased to or applied with 5 volts or VDD, which is equal to plus 5 volts. Now let us see what will be the voltage at VGSP and VGSN. Now 5 volts is here and source is also at 5 volts. Therefore VGSP is going to be 0 volts. Whereas here gate is at 5 volts, source is at 0, VGSN is going to be at 5 volts. So NMOS is on. For this case, NMOS becomes on, whereas PMOS becomes off here. Let us write it here. The NMOS is on. PMOS is now off because VGSP is 0 volts. The ground is connected to the output. So output is now at 0 volts. So for input voltage 5 volts, the output is at 0 volts. So we have shown that low input makes the output as VDD. A high input, which is namely the VDD or 5 volts, makes the output as 0 volts. Now let us try to understand how to draw the detailed characteristics of this in this particular topic. A CMOS inverter is realized by series connection of the P device and N device as shown in the figure. As we have seen here, both P device and N device are connected in series. And the main objective of this topic is to derive the DC transfer characteristics. The transfer characteristics is nothing but it's a characteristics between output voltage and the versus the input voltage. So we are going to derive this DC transfer characteristics for the inverter circuit. And here we have a table. I am going to present you the table, and that table shows the table outlines various regions of operation of both the N channel device and the P channel device. The next point is going to be the terminologies which we need to understand here is VTN, V sub T and sub N. So these are nothing but the threshold voltage of the N channel device. Typically the threshold voltage in micrometer technology it is 1 volt. However, threshold voltage depends on various parameters. As technology is miniatured, the threshold voltage also reduces. So similarly, the VTP, threshold voltage of the PMOS device, threshold voltage of P device or P channel device is typically minus 1 volt. And source, with reference to the above inverter circuit, source of the N device is at 0 volts, as we can see here from the circuit. The source of the NMOS is at 0 volts. And source of the PMOS device is at 5 volts, and VGSN is equal to Vin. We already discussed about this. VDSN is also equals to output voltage. VDSN is nothing but drain to source of NMOS device equals output voltage. Gate to source of PMOS device equals input voltage minus VDD. This will show a couple of seconds later. We will show the derivation of this expression. And drain to source voltage of the PMOS device equals Vout minus VDD. So this is, we have written here direct expressions, but we are going to show it shortly. So these expressions that are shown here, namely the VGSP and VDSP, are derived as follows. So now consider the gate source loop of the circuit. So let me show it here, the gate source loop here. In the circuit, this is the gate source loop, what we are considering here. Across the peripheral of the circuit is taken as gate source loop. In that, we have shown the voltages which are assumed to apply the KVL. Between the supply and the ground, we have a VDD, and the PMOS device, we have polarity as minus and plus with the VGSP, and plus and minus as polarity with the input voltage. If we apply the KVL in the loop that is shown here, this is the loop that we apply KVL. So we get an expression like minus VDD, we move in this direction, minus VGSP plus Vin, which is input voltage, equals to 0. If we rearrange these terms, we get VGSP, gate to source voltage of PMOS device, equals Vin minus VDD. This is the expression that I have written directly earlier, and now we have derived the same expression. Next, to obtain the expression for VDSP, let us consider the drain source loop. So drain source loop is nothing but the loop which is from outside this path particular direction. So all transistor output to drain and source is considered, and we have a supply voltage from VDD to ground. Okay, so now let us write the polarity of this device. We have a minus plus across the power supply, and across PMOS we have VDSP with the polarity as shown, and across NMOS output we have a V out. So now if you apply KVL for this particular loop shown, we have minus VDD when we move from this side in anticlockwise manner, minus VDSP plus V out equals 0. If we rearrange these terms, we get drain to source output voltage, drain to source voltage of PMOS device as V out minus VDD. So this is the expression for VDSP. Now let us show the table here. This table presented below relates the voltages of N device and the P channel device for all the three regions of operations of a CMOS inverter, namely the cutoff region, linear region, and saturation region. In the first column, we have shown here the type of device, namely the P device or N device, P channel or N channel device. We can also call this one as PMOS device or NMOS device. NMOS device. So now let us see that what are the conditions to operate this P device in cutoff region, linear region, and saturation region. Let us discuss one by one here. For the PMOS device to operate in cutoff region, certain condition has to be satisfied. Number one is the VGSP should be greater than the VTP. We already know that threshold voltage of PMOS device is minus 1 volt. Therefore, gate to source voltage of the PMOS device should be greater than minus 1 volt for the PMOS device to be operated in cutoff region. So the input voltage required to maintain this is Vin should be greater than VTP plus VDD. So VTP is minus 1 and the VDD is 5 volts. Therefore, Vin should be greater than 4 volts in order to operate P device in the cutoff region. Similarly, the other regions of operation of PMOS device are linear and saturation region. Let's go through the conditions required for the P device in the linear region. To operate PMOS device in the linear region, the gate to source voltage of the PMOS VGSP should be less than the threshold voltage VTP. VTP is minus 1 volt, therefore VGSP should be less than minus 1 volt. So this is the condition, first condition to be satisfied to operate P channel device in the linear region. The other conditions are the input voltage should be less than VTP plus VDD. So VTP is nothing but minus 1 volt and VDD is 5 volts. Therefore, input voltage should be less than 4 volt. Okay, so this is a condition that the input, if we apply voltage lesser than 4 volt, the transistor will be turned on, and to operate this in the linear region, we have to satisfy the next following conditions. So VDSP should be greater than VGSP minus VTP. So this is the condition to be satisfied by the P channel device to operate in the linear region. So VDSP can be written in terms of the input voltage. So we know that VDSP equals V out minus VDD. If you can substitute here, I'll show this derivation here. So what we have is so let me rewrite this expression. VDSP should be greater than VGSP minus VTP, and this can be shown as V out should be greater than V in minus VTP. V out should be greater than V in minus VTP, and this can be derived using this expression VDSP. This is the we want to prove that. So for that we need to have VDSP should be greater than VGSP minus VTP. So VDSP is nothing but we know that it is a V out minus VDD. This condition will keep it as it is, and VGSP is nothing but it is V in minus VDD minus VTP is kept as it is, and this minus VDD cancels with this minus VDD. We have left out with V out should be greater than V in minus VTP. The same expression is written in the table. Let's go back to the table. So as we have seen here, V out should be greater than V in minus VTP. V out should be greater than V in minus VTP. So we need to satisfy this condition to operate transistor PMOS device in the linear region. Let's go for saturation region. The condition required for the transistor to turn on is this. So VGSP should be less than VTP. VTP is minus 1 volt. If you apply across gate to source more negative than minus 1, then PMOS transistor will be turned on. This is for turning on the transistor. And to operate transistor in the saturation region, we need to satisfy other conditions. So Vin should be less than, at the input side, the input voltage must be less than VTP plus VDD. If we substitute typical values of VTP and VDD, so Vin should be less than 4 volts. So this is the voltage to be applied at the input for the transistor, P transistor, to operate in the saturation region. So the same equivalent version is written here. So VDSP should be less than VGSP minus VTP, and if we substitute VDSP as V out minus VDD and VGSP as V in minus VDD, we end up with this particular equation. So it means if we satisfy these couple of conditions here, then the P channel device will be operated in the saturation region. Likewise, we also try to understand how to operate PMOS, NMOS device in the cutoff region, linear region, and the saturation region. For NMOS device, it is very simple. So VGSN should be less than VTN, and this makes the transistor in the off state. VTN is typical value is 1 volt. When we apply at gate to source of NMOS less than 1 volt, the NMOS device will be turned off. So NMOS will be in cutoff region. Input required for this is input VGSN and Vin both are equal. Therefore, input Vin should be less than VTN. Vin should be less than VTN value. Typical value is going to be 1 volt. So these are the couple of conditions that we need to satisfy for the N-channel device or NMOS device to operate in the cutoff region. For NMOS device to operate in the linear region, we need to turn on the transistor first. For that, we need to apply gate to source voltage across NMOS device greater than the threshold voltage. This is the first condition. Also, this alternatively, this equation can be written as VGSN is greater than 1 volt. This makes the transistor turn on. Once transistor is turned on, then we can apply input voltage or try to maintain drain to source voltage less than the VGSN minus VTN. So this condition makes the transistor to operate in the linear region, and this can be written alternatively as V out should be less than VGSN is equal to V in minus VTN. So these are the alternate expressions here. So input required to operate in the linear region is input should be greater than threshold voltage, whereas VDSN should be less than VGSN minus VTN. So these are the couple of conditions that need to be satisfied to operate N-channel device in the linear region. To operate N-channel device in the saturation region, we need to turn on once again transistor. Same conditions will be carried forward. So VGSN should be greater than VTN, or VGSN should be greater than 1 volt. That is the first condition. At the input, we need to meet this criteria. Input voltage should be greater than VTN, or input voltage should be greater than 1 volt. Or lastly, the third condition required is the drain to source voltage must be greater than gate to source voltage of NMOS minus the threshold. This alternatively, this expression can be written as Vout should be greater than Vin minus VTN. If you are able to meet all these conditions, then N-channel device will be operated in the linear region. So with the help of this table, we understood what are the conditions required to operate P-channel device and N-channel device in the cutoff region, linear region, and saturation region. So once we understand this, then we can move and go ahead and plot the inverter characteristics. And let us see that what are the different methods to plot these inverter characteristics. The objective in this topic is to find the variation in the output voltage, which is labeled as Vout, which has as a function of the input voltage Vin. And this can be done by three methods, namely the graphical method. We are working out on the graphical method. Other methods are analytical methods, and through simulations also we can plot inverter characteristics, transfer characteristics. But however, we are going to choose the graphical method as a procedure to plot the Vout versus Vin characteristics. Here, given the input voltage Vin, we must find what is the output voltage, and there are conditions that need to be satisfied. The first condition is the drain to source voltage of the NMOS device should be equal to drain to source voltage of the PMOS device. Since PMOS device drain to source current is negative, we here include an absolute value to show it is a positive current. So the condition required is to plot Vout versus Vin. The IDSN should be equal to IDSP, and also the threshold voltage of the PMOS device should be equal to the threshold voltage of the NMOS device, with of course negative for the PMOS device. And also width of the transistor is very important, since electrons and holes, these two charge carriers, will not be moving at the mobility of these two devices is not same. Therefore, electrons moves at higher speed compared to the holes. In this context, to make the operations symmetrical, we need to choose width of the PMOS 2 to 3 times larger than the width of the NMOS device, and this ensures that the performance parameter like beta n will be equal to beta p. Once we are able to maintain this, then the beta n will become equal to beta p. Therefore, the inverter will be operated in a symmetrical manner. Okay, we'll see that later on what do you mean by symmetrical manner. Okay, so let us go through the currents here. We begin graphical representation of simple algebraic equations using this here. For the currents here, what we are showing here, the drain to source saturation current should be equal to beta times the VGS minus VT. This is called effective gate voltage, and that is multiplied with the VDS, okay, minus VDS square divided by 2. So this is the expression for the current drain to source current in the linear region. And in the linear region, the same equation can be rewritten as IDS equals beta times this VGS minus VT. We can label it as VGT. So therefore, this expression becomes beta into VGT minus this VDS is taken out. So therefore, VGT minus VDS by 2, and that's multiplied with VDS. And this is the drain to source current flowing in the linear region. When VDS is less than VGS minus VT, this is the condition required to be satisfied for the linear region of operation that we have seen in the table. Or shortly we can write this one as VDS should be less than VDS sat. This is the current that flows in a transistor of NMOS in the linear region. The current in the saturation region is as follows. The drain to source saturation current is now beta by 2 times VGS minus VT whole square. This can be written as shortly as beta by 2 into VGT whole square. And the condition required to maintain the transistor in saturation region is VDS drain to source voltage must be greater than gate to source voltage minus the threshold voltage. Alternatively, this can be written as drain to source voltage should be greater than drain to source saturation voltage. So these are the conditions required to operate transistor in the saturation region. Now let us plot the characteristics. Since we are following graphical method to draw the inverter characteristics, we need to plot N device and P device characteristics separately. So let us plot for the N device. For N device, we are going to show a graph of IDSN versus VDSN for various gate to source voltage for the NMOS transistor. Similarly, for the P device, we are going to plot drain to source current of the PMOS device versus drain to source voltage of the PMOS transistor for various values of gate to source voltage of the PMOS device. So let us see this plots graphically here. Here is a plot for both the transistors for both PMOS and NMOS transistor. For NMOS transistor, since voltage VDS and IDS are positive, so the graphs or characteristics falls in the first quadrant as we are seeing here. This is for the NMOS device characteristics, drain characteristics. Similarly, for the PMOS device, since voltages VDSP is negative, IDSP is also negative, so therefore the characteristics falls in the fourth quadrant here. And here we are plotting various family of curves for different values of VGSN. This is VGSN1. This is the first gate to source voltage. Say for example, we are choosing here as 1.5 volts, and this has 2 volts, 2.5. This has 3 volts and 3.5. Notice that the currents here are not same. So for VGSN is equal to 1.5, the current is less, and as we increase the gate to source voltage from 1.5 to 2 volts, the current is increased proportionally. So this height will tell you the drain to source current of the NMOS device. So you can see here the distance here is not same as the distance here. So there is a larger current flows as we increase the gate to source voltage of the NMOS device. Current is flowing in an exponential manner, therefore the distance between these two characteristics are not same. So based on this, we can also show the PMOS characteristics, which falls in the fourth quadrant. Here we choose VDSN as 0 to 5 volts. We can even show incremental values like 1, 2, 3, 4 and 5 volts. Okay, so these are the various values of VDSN, and VDD is nothing but 5 volts. In similar lines, we can also show VDSP values for PMOS device. Okay, so this is -1, -2, -3, -4, and we have a -VDT, which is -5. So we have different values of VGSP here. VGSP1, let us take it as this value as -1.5, second one as -2, this curve as -3, -2.5. Let us go in steps of 0.5, -3 volts, and lastly we have VGSP5 as -3.5 volts. So we have different gate to source voltage. As we can notice, similar to this here, we have different currents keeps increasing negatively as we increase the gate to source voltage of the P channel device. And here we have, in a single plot, we have shown both the characteristics, drain to source characteristics of NMOS device and the PMOS device. So with the help of this plot, let us draw the inverter characteristics. Now the next step in to draw the inverter characteristics is we will try to flip this characteristics from the fourth quadrant to the second quadrant by making IDSP as positive, and that is shown in the next characteristics. The absolute value of P transistor drain current IDS inverts characteristics. This allows voltage current characteristics of P device to be reflected about the x-axis, as you can see here. So we have IDSN for the NMOS device, whereas for the PMOS device we have a modulus of IDSP. So we have flipped to the second quadrant the PMOS characteristics, and let us retain the same voltages that we have discussed earlier. So this is 1.5 volts, This is 2 volts, 2.5, 3 volts, and here we have 3.5. Similarly, here we have minus 1.5 as VGSP1, minus 2 volts, minus 2.5, minus 3 volts, and here lastly we have minus 3.5. So here we are showing here the NMOS characteristics is not changed, and this is the NMOS drain characteristics. We have seen here various family of curves, whereas PMOS characteristics we have flipped from third quadrant to second quadrant. So here we have PMOS characteristics. Okay. Next, we will try to shift these characteristics to the first quadrant to have a commonality between the PMOS device and the NMOS device. We'll show you how to shift from the characteristics from the second quadrant to the first quadrant. Notice that here the x-axis is drain to source voltage VDSN, and here we have minus VDSP, that remains same. We have not changed this, whereas current only has become now positive. And now let us see, when we shift this characteristics from the second quadrant to the first quadrant, we can identify the intersection points, and that is shown here in this graph. You can see here. Okay, and here I will try to show the PMOS characteristics with red color so that you can understand. So once you shift this PMOS characteristics here, the curves are going to be like this. This is again freehand drawing. Okay, let us show a rough graph here. Okay, and this is the second one. This is the third PMOS characteristics, and we have a fourth one. This is a fourth one, and last one of the PMOS device are as follows. Okay, and we already know that for NMOS device we have a graph of VDSN, which is 0 volts is here for NMOS device, and 5 volts, this is for NMOS device, and we have various values of VGSN1, VGSN2, 3, 4, 5, and VGSN is also equal to input voltage VIN1, VIN2, VIN3, VIN4, and VIN5, and we have taken typical values as 1.5 volts here, 2 volts, 2.5, 3, 3.5. These are the VGSN or VIN values. And now we can observe here, earlier this was the, once you have flipped and shifted this value here, we need to add with VDD. Therefore 0 with VDD, when we add here, this will be VDD point, and here the VDD minus VDD cancels, and we have a 0 point here. This is for the PMOS. So PMOS will start with 0 here and end with VDD here. And now for a PMOS, earlier we have a 3.5 volts here, but VGSN or VGSP, I would like to write here in the VGSP equation. So we have equation like VGSP, we already derived this, equals Vin minus VDD. Now let us try to find out what is Vin. Vin equals VGSP plus VDD. Using this equation, we can find out what is the input voltage Vin. So VGSP, this is VGSP. VGSP earlier was 3.5 volts for PMOS device, and VDD is minus 3.5, of course here, not a positive. So this is minus 3.5, and VDD is 5 volts. Therefore Vin becomes 1.5. So we have shown here Vin as 1.5. Similarly, earlier value of this is VGSP4 is 3 volts, Substitute here 3 minus 3, of course, minus 3, this is minus 3 minus 3.5. So minus 3 plus 5 gives you 2 volts. So we have here V in 2 as 2 volts. Similarly, here we have minus 2.5 as VGSP earlier value, and that is converted to input voltage as plus 2.5. Similarly, this is 2 volts minus 2 is now minus plus 3. Okay, so using this equation we can convert to the input voltage, and lastly we have VGSP as minus 1.5, that is equal to input voltage 3.5. Now it's very important now to draw the inverter characteristics. We have input voltage here, we have V in 1, V in 2, V in 3, V in 4 and V in 5 namely, and to plot output here, so we need to find intersection points of this V in 1 1.5 volts with the PMOS V in 1. This is the NMOS 1.5 volts, and PMOS 1.5 is here. So the intersection point is somewhere here. Okay, it is something like this. I would like to show here with a different graph. Okay, so we have drawn here both NMOS and PMOS. Let me show the NMOS in green color. So here we have 1.5 volts as input voltage V in 1, whereas PMOS, it is 1.5 is somewhere here like this. So this is V in 1 equals 1.5 volts is here. You can see the curve here. V in 1 1.5 is here for PMOS. This is for the PMOS, and the green color that we have shown is for NMOS. So the intersection point is somewhere here. Now if we draw the vertical line downwards here, we get VDSN. VDSN is when we draw vertical line, which is here itself we have a 5 volts. We can maintain a table for this. So let us write a table for this. We have a V in and we have a V out. Starting with 0 to say 1.5, though we have taken here straight away 1.5. Once we drag here vertical point, we get VDSN as VDSN is nothing but V out, and that is equal to 5 volts. And let's move to the next input value, which is 2 volts. VGSN 2 or V in 2 equals 2 volts, and the corresponding V in 2 is here 2 volts, and intersection of this is very close to the the VDD, which is let us say here this is 2 volts. So 4.8, let us say this is very close to the VDD. 4.8 volt is going to be the output voltage. The intersection point somewhere here. Okay, similar to the one I have shown here for 1.5, we can also show for 2.5. NMOS 2.5 is here, this curve, and for PMOS 2.5 is here, exactly at the mid. They intersect here. So for 2.5, it is a 2.5. It is a 2.5 volts. Next, let us move to the 3 volts. When V in 4 equals to 3 volts here, this is for the NMOS, and 3 volt is here. Now you can see that it has moved close to the low voltage. VDSN is now very close to 0, let us say 0.5. So at 3 volt input, VGSN or V in, the V out or VDSN, this is equal to VGSN, and this is equal to VDSN. So for 3 volt it is say 0.5 volts, and lastly for 3.5 As we can see here, the intersection will become very close to the 0, because for NMOS it is the last curve. For the PMOS it's going to be here, the bottom curve here, the one which is shown red color. The intersection point is very close to 0. So you can say here for 3.5 the output voltage is 0. Now we can observe this table. From 0 to we have gone all the way up to 3.5, increasing order, but you can see here the voltage has been dropped here. That means the inverter transfer characteristics is somewhat like this. So now we'll draw the inverter transfer characteristics. So the inverter transfer characteristics is as shown here. We have x-axis as Vin, input voltage, and y-axis as output voltage, and x-axis can be divided into the 3 strips here. From 0 to VTN, this value is 1 volt, and here we have VDD by 2, this is 2.5 volts, and VDD minus VTN, which is 4 volts, and lastly VDD equals 5 volts. Like this we can divide the x-axis time frame in this way, and y-axis is divided into the just two values, VDD by 2 and VDD. Now we can plot the transfer characteristics. So from 0 to 1 volt, so as we can see from the characteristics, from 0 to 1 volt or 1.5, output remains at 5. So you can see here the output remains at 5, which is 5 volts here. And as we move from 1 to say 2.5, 1 to 2.5, output drops at 2.5, exactly drops. You can see here that 2.5 it exactly transitions happens from high to low, but you can see here it is decreasing, okay, as we keep increasing the input voltage, okay, and at 2.5 it drops, and when the input voltage is increased beyond 2.5, we can see it is coming close to the 0, and further it goes to 0 when the input voltage is increased. So in all this, in the entire transfer characteristics, we have divided into the 4 segments, 0 to VTN. In this segment you can see here PMOS is on, okay, whereas NMOS is off, because we can see that for NMOS device threshold voltage is less than 1 volt, therefore NMOS remains in off, PMOS is going to be on, and PMOS remains in the linear region, NMOS remains in the cutoff region. This also can be seen from the characteristics. Here in this region, NMOS is going to be when the 0 to VTN. So 0 to VTN means somewhat here, 0 to VTN. Sorry, this is input voltage 0 to VTN, 1 up to 1.5 or 1 voltage less than that. So you can see here, and NMOS is going to be off, because in this region it will be in the cutoff, whereas PMOS will be in the linear region. As we can see, curves are increasing here, so therefore PMOS will be in the linear region. So this is clear, NMOS will be off and PMOS will be in the linear region. Okay, NMOS is nothing but it is the voltage is less. In the next this region, this segment can be called as A segment, and the next segment can be called as B, and C is exactly at 2.5, and the next one is D segment between 2.5 to 4 volt. It is a D segment, and from 4 to 5 it is an E segment. And in each of these regions we need to understand which transistor is on. From 1 volt onwards, as we can see here, from VTN 1 volt to 4 volts, both transistors PMOS and NMOS are on, and the region of operations are going to be different. In the B segment, we can see that the P is in linear, N is in saturation. So in that you can easily understand from the curves here. In the B segment, as you can see that when the input is dropping, so the P is going to be linear, and NMOS are also, they are going to be straight line, they are in saturation. So you can see here PMOS is linear, NMOS is in saturation. At exactly transition, both are going to be in saturation. In the D segment, the PMOS is in saturation, NMOS is going to be linear. So we are now moving to this area. NMOS is going to be in linear, PMOS is going to be in saturation, and in the E segment, PMOS is going to be in cutoff, NMOS is going to be in linear. So in this particularly the segment, Okay, the PMOS is going to be in the cutoff, and NMOS is going to be in the NMOS is going to be in the linear region. As we can see, NMOS curves are going to be linear. Okay, so we can also show the current graph. Current, whenever the transistor is making a transitions, inverter is making a transition, the current is going to spike. It's going to be from 0 to 1 volt, and from 1 to 4 volts you can see that the current is going to spike up, and it is going to be peak at exactly 1.5 when the inverter is making transition, and later the current drops and it goes to 0. So this is the current graph of CMOS inverter. And now, as we said already, the summary of inverter operation can be shown in the form of a table. We have a totally